Assalamualaikum sir. I am Farzan Hassan Shumi. Today I will explain a simple car parking system using a block diagram and flowchart. We are considering a parking lot with a maximum capacity of 11 cars, that is 2 plus 5 plus 2 plus 2, 11. Block diagram. The process begins with a keypad where the user inputs data. This data goes to an encoder, then to a register, and finally to a comparator to check it if the parking is full or space available. We also use a clock and a counter to keep track of time and the number of cars. Entry and exit sensors detect whether a car has entered or exited. Based on that, the counter updates the car count in the register. Two timers are used. Timer 1 activates the full display when the lot is full. Timer 2 activates the space available display where parking is available. Flow diagram. The system starts with the keypad and uses sensor to detect the car movement. If a car enters the system, check. If true, it increments the car count. If false, it decrements the count, including in exit. Then it compares the car count with the maximum value, which is 11. If the count equal 11, it display full. Otherwise, it display space available. This system helps efficiently manage a small parking lot by using sensors, times, and logic to show real-time status. Part of the explanation focus on the technical functionality of our parking system using both the block diagram and circuit diagram. The block diagram shows how all the components are connected, like the keypad, sensors, counters, timers, and display units. It gives us an overview of how the system is structured. The flow diagram, on the other hand, explains the logic behind the process, how the system responds when a car enters or exits, and how it decides when to show full or space available. At the heart of this system is a 4-bit up-down sensors counter, which is shown in the circuit below. This counter is triggered by enter and exit sensor. When a car enters and space is available, the count increments. If a car exits and count decrements, once the count reaches the maximum value of 11, the system displays full and no more cars will be allowed to enter. This ensures the parking system runs smoothly, avoids overfilling, and gives real-time feedback through the display system. Today, I had like to explain a system that uses two timers, one in monostable mode and the other in stable mode. In this system, the monostable timer is used to control the display of the word full, which appears only once when triggered. On the other hand, the stable timer controls the blinking of the message space available, which continues to blink as long as the condition is met. This blinking behavior is possible because the stable timer produces a continuous output, which is prepared for signal avail space in dynamic way. We also calculate the duty cycle of the signal using the given values. We found the data cycle to be 64 and the frequency to be 6 Hz. This means to signal blinks 6 times per second. This kind of timer logic is commonly used in electronic display system to alert users in real time, such as in parking systems or digital counters. Let me now explain the second part of system, which focus on the stable mode timer used for displaying the message space available. In this configuration, we have set the timer to operator in stable mode, meaning it continuously switches between high and low status, creating a square wave output. This is what makes the message blink repeatedly. We calculate the time period T as 0.167 seconds or 167 millisecond. The high time and low time were determined based on a 64% duty cycle. So that high time comes out to approximately 106.88 meter second, and the how time is 60.12 meter second. Using these values, we calculate the required resistance for out circuit. Lower resistance R2 is equal to 1736.06 ohm. Upper resistor R1 is equal to 1348.49 ohms. We also used a capacitor of 250 ohm in timing circuit. The diagram at the bottom of the page shows the stable mode setup where the timer IC is connected to resistor and a capacitor to produce the necessary pulses. The pulses are sent to a display circuit that shows space available in a blinking fashion, making it easy to grab attention. This kind of setup is commonly used in parking system, counter, or any application where visual signaling is important. Let me now explain the final part of our system design. In the figure mentioned, we have two values. I represent the value of the resistance connected to keypad. B represent the value of the resistor connected to the center of or control unit. Since the full display is meant to be contents and not blinking, we have decided to use another timer in a stable mode to manage the display of other messages like space available. To ensure smooth and reliable operation, we have designed the system by adjusting the duty cycle. This way, the output signal can be tailored as need. In this part of the design, we are considering the high time as a 167 meters second, the low time as a 0. Because of the setup, the lower resistor R2 becomes 0. The upper resistor R1 is calculated using by formula R1 is equal to THO 0.693 times. Substituting the values, we get R1 is equal to 167 times 10 to the power minus 3 into 0.693 times 50, 10 to the power minus 6 is equal to 4819.628 omega. These values ensure the timer outputs a steady signal suitable for the full indicator with any blinking, ideal for continuous display. So in summary, we used a combination of monostable and a stable timer to control how messages are shown, using appropriate register values to shape the timing behavior. In this setup, we use a timer circuit most likely based on the 555 timer in a stable mode to generate a continuous square wave signal. This signal controls the logic operators in circuit. The output from this circuit timer circuit is used to drive a comparator that comparators two values A and B. A is the value stored in the register connected to the keypad. B is the value stored in the register connected to the counter. The main function of this circuit is to activate a display level full whenever B is greater than or equal to A. This means the system can be used to monitor capacity or quantity. For example, in a digital storage or inventory system, and show a full integration when a limit is reached. So this project combines a timer, logic gates, and a comparator to implement a simple and useful altered system based on input values. In this part of project, we are focusing on the timing stable behavior of the system. We begin by noting that the clock period is 1 millisecond. The timer operator with a high time of 106.88 millisecond and a low time of 60.12 millisecond. This means the timer remains high longer than it stays low, which is essential for how the circuit responds and the transition between states. Now we look at the states table provided. It shows how the system behaves based on current states and input current values. There are two main states, so SO and S1, S0 and S1. The system transition between these states depending on the counter value. For instance, while in states S0 and for counter values 0 to 2, it remains in S0 and produces an output of 1, 0. However, at counter value 3, the state changes to S1. In S1 for counter values 0 to 2, it stays in S1, but when the counter reaches 3 again, it transitions back to S0 and the output becomes 0, 1. This cycle behavior helps the circuit manage and reflect the changing input condition, possibility to toggle the full display or other indicators depending on logic condition. In summary, this table guides us through the system's sequential logic, ensuring we understand how states change over time with input and how output is controlled accordingly. Let me now walk you through the state diagram and the Verilog HDL implementation of our finite state machine or FSM. We designed a two-state system S0 and S1 to control the blinking logic of two output and A and B. The transition are governed by a counter. In states S0, the output is A is equal to 1 and B is equal to 0. The system stays in this state as long as the counter is less than 3. Once the counter reaches 3, we transition to state 1, state S1. In state S1, the output switches, A becomes 0 and B becomes 1. The system stays in S1 while the counter is below 3 and moves back to S0 when the counter hits 3 again. This forms a loop where the output toggle every 3 clock cycle. Now looking at the Verilog code implementation. The module is named FSM Blink. In takes a clock and reset as inputs and produce two outputs A and B. We declare 3-bit counter and a single bit stator register. On reset, the FSM initialized the state is set to 0, counter is cleared, and the outputs are set to A is equal to 1, B is equal to 0. On every positive edge of the clock, the counter increments when it reaches 3. It resets and the FSM toggles to the other state. Based on the current state, the outputs A and B are updated accordingly. This FMS demonstrates a blinking pattern control pulled by digital logic. It highlights how we can use state machines and hardware description language like Verilog to implement timing-based logic that would otherwise require manual toggling or external control. There are plenty of limitations for the developed system. There is a point of issues that areas which is that the counter is not modified to only counter 11. Since it is a 4-bit counter, it will go up to 15. So if a car comes in desperate, will increment the counter for a greater capacity. The counter needs to be a higher bit 7. The number that is given the declare has to be increased accordingly. The regrets need to be adjusted as well. The specific of which bit to use depends on the increment capacity. Thank you, sir. That was my